Okay, perfect. So we can continue. So our next talk will be by Danae about GroMiT. Please go ahead. The floor is all yours.
Thank you. So yes, I'm going to be talking about GroMiT. It is a growth and migrations track code that we have been developing literally the last maybe year and a half. So it is a very new code. Very much in development. Still, first version, a first stable version, we have published the a user guide of how it can be used. And although it is not public currently, because it was supposed to be public like last month, but I didn't get the time to sort it all completely. For sure, for collaborations, if anybody asks me the code, I will just send the code, to be fair. And soon I hope it's also going to be public. So it kind of started because we wanted to have a self-consistent Mercury Archaeos code that Diego was talking before. So it was born as a plugin for that, and then it kind of it took a different way at some point because we had a lot of requests from the GAPS consortium to basically track the formation histories of the observed planets. I don't know if you know GAPS. It's a collaboration that uses observations. Basically, they do high resolution spectroscopy around stars and characterize exoplanets. To begin with, in its original form and the simplistic form, it is a Python code. It is based on the pebble accretion theory, and it does come at the moment in two flavors. There is the single planet mode, and there is the population synthesis code. It is based on the works of Johansen, Tanaka, Lida, Armitage, Ida, and Turini et al. In bits and pieces, they have been taking as the code grows and we see that there are different needs for it. We accumulate equations as much as we can. The way it works is we basically initialize the initial parameters, and then it goes on to calculate the mass accretions onto the star and on the pebbles, and then we fix the physical characteristics of the circumstellar disk. It goes through, it calculates the pebble isolation mass and the gap mass, and it then focuses on the planet, its core accretion, its migration, then the envelope contraction, and then it goes to the rapid gas accretion and type 2 migration, and it gives us the result. This is the single planet track mode. So for the initial parameters that the user can actually define, you have the initial time for when you want the code to start tracking the planet as it forms. You have the time step for the tracks, and of course you have to give it a final time for the simulation to end. And you can change the mass, the stellar mass, the stellar luminosity, the mass accretion rate, and we also have the mass loss due to photoevaporation, although that is still not very well tested. Then, of course, you need to define your planet properties. So you need to put your initial core seed at some semi-major axis away from the star, and you need to build your disk. So you need to give it the characteristic radius, you need to give the surface density, the disk radius, the exponent of surface density, the alpha parameter for the disk, and you need to give some also dust properties like the dust to gas ratio and the pebble size. So there is a few things that can be there's a disk temperature that it can either be parametric, as in Johansen et al. 2019, or it can be analytic using the equations from Ida et al. 2016. There is in the initial parameters file, the user basically can choose what they want to do. Then it basically, this is following the chart, the flow chart that I showed before. What the code goes into, it goes through the gas drift velocity. Well, actually, these are the side equations, sorry. So we're also using side equations to help us define the disk parameters, well, the disk parameters more than anything else. So we have the gas drift velocity, we have the accretion rate onto the star, we calculate the disk viscous parameter and the radiation temperature. We have the Hill radius at the two-dimensional regime, and then the things that you need to build up your disk. And then the way it works is that as any simple code, you initiate your parameters, you start a time loop, and it goes through the mass accretion on the star, the disk temperature at that point. We use the condensation sequence of solids to set up the pebble density. That's from Torino 2023. We set up the pebble accretion. We're using the generic radial drift from Weiden-Schilling in 1997. We calculate the surface density of the pebbles and the isolation mass and the gap mass as Johansen in 2019 do. And then we split depending on the mass of the planet. When it's still just the core, then it goes through its growth accretion and the type 1 migration. While it is less than the pebble isolation mass, then once it is bigger than the pebble isolation mass but smaller than the gap mass, it does the envelope contraction and still type 1 migration. And after that, it goes into the rapid gas accretion if it arrives at that point, and type 2 migration. And the result is something like this. Basically, you end up with a file that contains, for every step, the time, the semi-major axis, the planet mass, all these variables that I'm listing here, and the plot that is only one track. This is just the combination of too many tracks that we run because, as I said, we found that it has a lot of applications to check the formation history of observed exoplanets. And so we were starting to look into that. So defining a disk that has a certain parameters, depending on where you begin your, where you input your initial seed, you end up with completely different results in terms of the final planetary mass and location, as it would be expected, of course. And so the second step was to make population synthesis mode, which we weren't planning to, but it was a natural evolution, I suppose. And it is simply Monte Carlo realizations of on top of the main code as GroMiT. So the only thing that changes basically is the input in the input file. You have to set up how many planets you want to, well, not track, but track. And then you put a range for the initial point of the initial time where you put the seed. So you might start having a core at 0.1 million years or at 2 million years. As depending, you can choose, the user can choose the range, and the same thing for the final time when the code stops. And you can also have a range for the initial semi-major axis for the core seed, and you can also change the alpha parameter. The rest of the parameters at the moment remain as in the original GroMiT, although we are planning to extend this and to see what else we can change and what that result would be on the planet. But as I said, this is a very new code, so we're still also trying to understand the output. We have been, however, using it Okay, sorry, before I say this, you end up with a text file that has the summary of of the disk as you have set it up, and as well as a file that for every planet that you have simulated, it contains some parameters that we find interesting and we want to look further into. Like, for example, the initial semi-major axis, the final semi-major axis, the planet core and envelope mass, the temperature that you might have on the disk at a given. I think actually the temperature is at the final run or at the initial run. I have to admit I don't remember this. I need to check it. So you end up with a plot like the one I'm showing here, where depending on this is the final orbital region, so where your planets end up being at the end of the run, and that is the resulting masses. And you can change I didn't put that. You can also change the grain size, because that is in any case a user-defined input from the very beginning. So depending on it doesn't have a continuous range, but you can have it as 0.1 millimeter or 1 centimeter, and see what differences that results into with regards to the planets that you can form. So we were asked to apply this in observed exoplanets. So this is one of these tests in the planet TOI 387 that is located at 0.8 AU. And you can see how it is useful very much so to first run the GroMiT to explore a wide range of possible initial setups for the disk and the evolution of the planet. And then once you have your final answer, your final population synthesis plot, then depending the mass of the observed planets and the error bars, this is basically the error bars of the measurements for the location of the planet and its mass as measured. You can see several solutions of possible tracks that the planet might have used in order to arrive to its final mass. So it is very much a degenerate problem. As you can see, like there is at least 3 different initial positions. So 3 different initial setups for the disks that can produce a disk that is, that can produce a planet that is more or less within the error bars of the observed characteristics of the planet. It is also very, very useful for comparative planetology. So basically, when you have more than one observed exoplanet, so this is another 3 examples that we have published, or one of them is being in the final stages of its review process. And again, it's the same idea. We run the population synthesis. We can change from millimeter to centimeter sized pebbles, and we can find a range of possible initial setups that can give us results that are within the error bars of the observed exoplanets. So some of them we can discard, others not, depending. Like, for example, if we have a solution for the outer for the inner planet that was starting its initial position was further out from the outer planets, and then it would have had to jump over it, for example. So, we can discard some of these or see what else have happened to the disk. And of course, given that we know the tracks, the distances that they have flown, they have migrated within the disk, you can also tell something about the chemical evolution, although that is very much still work in progress. This this code itself does not give you the chemistry. It just only tells you which regions of the disk the planets have crossed, and the potential chemistry that they could result in from that. And I will leave it at that. That is all. I mean, we're still building it, actually. I should have said, these are all serial codes. It is quite fast. I mean, for 50,000, the Monte Carlo one there, for 50,000 planets, it takes a few hours depending on the resolution that you want, the time step for that you choose, and we are in the process of parallelizing it. And yes, that is all. Thank you.
Yeah, thank you very much for this very, very interesting project. The talk is open for questions. Maybe I can ask a question in the meantime. So is my understanding correct? This is mostly like for planetary masses and radii, but you don't include the chemistry at this stage yet. Or I assume this is something that you want to do in the future. Could you comment?
Well,
on
the
it?
plan is that we're going to join this both with Mercury Archaeus, which actually we're almost there, and also with Jade from Elenia that she was explaining before, in order to have also the chemistry of the disk. But at the moment, it is simply that, well, if the core started forming at 10 AU, it will have a different composition than if it started forming at 1 AU. So we have the sequence of we have the snow lines across the disk that it passes. So we change, for example, the density of the pebbles according to that. But no, it doesn't. It's not going to tell you that the actual chemical composition.
Yeah, no, of course. Very cool. Then I have a question for this. So for this example that you show here for this TOI 2443. So I assume these are like two different, like basically many different simulations that you use to match the planet B and the planet C, or is there like some option where you say that you actually have both planets growing in the disk at the same time, but maybe they just don't interact gravitationally?
And no, that at the moment, GroMiT only runs for a single planet, so they have to be multiple planets in order to make. We have some ideas how to run it with, well, at the moment, 2 planets in the disk, but time is what it is, and we haven't had time yet to actually implement this. But so for the moment, yes, it is just individual runs of the code for each planet.
Yeah, no, absolutely. Okay, cool. Thank you for the clarification. Are there any other questions in the meantime? Yeah, Andre has a question.
Hi, thanks for a very interesting presentation. So I'm just wondering, in all these examples that you showed, the migration tracks of the planet are always directed inwards. Do you ever get solutions in which, like, the planet spent part of its orbital history migrating outwards, for example, in the Type 1 regime?
No, surprisingly enough, no.
And why is that? Is that because of the assumptions for the underlying disk?
I think so. I think it's how we basically set up the disk. But yeah, I cannot give you a more exact answer to that.
Okay, thanks.
And it might be related also to the viscosity, because if the viscosity is very low, a lot of these co-rotation torques, they don't really work anymore.
I mean, possibly. We've been trying to use the viscosity ranges that we're using tend to be from observational ranges. So we don't just pick and choose whatever. We try to keep as close to the observational values, with all the caveats, of course, that contains, because also observations come with errors. But I mean, otherwise you could tell whatever. So we try to use the observational parameters or close to the observational parameters where possible.
Thank you. Are there any other questions? This does not seem to be the case. So thank you very much.
Welcome. Let me stop the share.